All right, so this is what you guys have picked up so far from the Java Labs. This is basically what I wanted you guys to figure out anyway. So the first thing you guys should be noticing is that when we are talking about covalent bonds, we're talking about shared electrons. When we talk about ionic bonds, the electrons are getting transferred, and then we have a positive and negative, and the electrostatic attraction is what makes the ionic bond. So this is slightly different, and in fact, we'll learn next week the deciding factor on what decides something is going to be an ionic bond versus a covalent bond, which is interesting. All right, so I'm just trying to think which ones I want to show you. Let's do, which ones do we got there? Let's do water. Go back. All right, we want that one. We want this one. We want this one. Okay, so here's water. What we can notice with the oxygen is it has 1, 2, 3, 4, 5, 6 electrons. The thing to keep in mind is that this is talking about valence electrons. So if we go to the water molecule here, you see how it actually has 8 electrons because you have 2 more in the inner shell, but we're only concerned about the outer shell when we are talking about Lewis structures. So that's why we have the note on there. Electrons are only shared in the outer shells. That was contributed by Emily, who refused to type it, to write it. You should just written it down. Okay, so when we're looking at these guys, the other thing that we notice is that they're sharing electrons to become stable. So for example, that's bonding, and then that's bonding over here. And same thing when we're looking over here, that's bonding over here, that's bonding over here, and now they're a lot happier, okay? So everything we're thinking about is about stability. The other thing that you guys would have noted is that they needed 8 electrons to be stable. That's more or less true. It just depends on the molecule. There's going to be a couple of exceptions to the rules. One of them we can already see, which is the hydrogen here. So hydrogen only needs 2 electrons in its shell to be stable, which makes sense because it only has the 1 shell. But everybody else has 2 electrons that it's going to need. So this guy, sorry, not 2, 8 to get stable. Cool. And that's the same we see over here as well. Right, when we are building some things that are larger atoms, like our ammonia, in this case, actually, let me break it apart. So you see with ammonia, it has 1, 2, 3, 4, 5 valence electrons. We want to get up to 8, so that means it has 3 bonding spots, which makes sense to why this is now taking 3 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. When we looked at water, it had 1, 2, 3, 4, 5, 6, so we needed 2 more to get to 8, so it only has 2 more bonding positions. Are we good so far? All right. Carbon's actually really special. So carbon is the building block of life. We don't have time in our level 2 course to do organic chemistry, but you will do organic chemistry in the level 3 course. And organic is an important building block to life because when you look at our with carbon, you see how there's only 4 electrons. That means it can have 4 bonds. That's the maximum amount of bonds you can have in an atom. So it makes it a really good building block because then I can start putting these carbons together as a chain. You see what I'm saying there? And then we can stick in the hydrogens and stuff. So it gives us a lot of options when it comes to building our atoms, or sorry, building our molecules. So when we talk about organic chemistry, we talk about carbon-based chemistry, which you guys will do next year. All right? So it's the smallest atom with 4 valence electrons. Everybody else doesn't have that same ability to bind. So this guy only has 2. The nitrogen only has 3. There is theory that we could have nitrogen-based life because 3 could potentially build enough variation in molecules to make life, but it's unlikely. The other one that has been proposed as a potential life-based molecule is, or life-based atom is silicon. Silicon is down 1 for the periodic table from carbon. It also has the 4 bonding sections, but it's a slightly bigger atom. Because, again, it's a bigger atom and it's found in a smaller frequency, it's probably not likely to be a building block for life, but it could have that potential. So that's just some interesting facts for you. All right, let's talk about how we decide to build some of these molecules. So, for example, we have carbon dioxide over here. So the carbon's the 6.
I had that exact same problem.
Fine, you go over there, you go over here. Just doesn't want to move the carbon. Okay. So do you see how in carbon's sake, you have 4 electrons here, 1, 2, 3, 4, 5, 6 electrons here, and 6 electrons over here. So what we're trying to make up is 8 for each one, and we're going to run into a problem in a sense that if I just bond 1 together, that's not going to be enough. So what you should notice is that you see how in this bond, there's actually 4 electrons instead of 2. Whereas when we looked at this guy, there was 2. So what we see here is a double bond forming. So instead of just sharing 2 electrons, it's sharing 4 electrons. And we're going to talk about how do we know when that's going to happen. Are we okay with that so far? So that's what we're looking at logistically. So let's go through some of the notes. So when we are trying to draw Lewis structures, we need to have two bits of information. The first bit of information is what atoms I have, and the second bit of information is what is their electron valence shell and how many they have in there. So you're going to need a periodic table to find that out. I have forgotten to print them, so we're just going to look one up. All right, we'll do ammonia first because I like ammonia. It's a simpler molecule, and then once I do ammonia, I can start doing more complex molecules that have double and triple bonds. All right, so first thing when we're talking about ammonia, just trying to choose a color you guys haven't chose. All right, so we have ammonia, which is NH4. No, 3, lie, 3. Sorry, I'm lying to you guys. All right, so first off, I need to be mindful is what do I have with my atoms, how many I have, and what number of valence electrons they have. So if I have nitrogen, number of atoms, I have 1, and then valence electrons. When I look at nitrogen on the periodic table, we see that it's in group 13 over here. So that tells me it has, or not 13, 15. That tells me it has 5 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Group 15, 5 electrons. So 5 valence electrons. So when it comes to what I can do bonding-wise, nitrogen can contribute 5. Then I have my hydrogens. Hydrogens, I have 3 of them. Valence shell for hydrogen only has 1 electron. It's the smallest of our atoms. So 3 times 1, I have 3. So total number of atoms that I'm working with is 8. Are we good? Do you need a pep track? We're okay. All right, so with when I start setting up, so there's 2 methods on how you can do Lewis structures. I'm going to teach you the method I prefer because it will be the one you use next year for level 3 chem. The method that is written in the SciPad does work. It is really good, but the problem is the moment you go into level 3 chem, it doesn't work anymore because the molecules get expanded and get more complicated. So that's why I'm teaching you this method. But if you want, you can learn the other method too. All right, so the rule is, first step is that I need to put an atom in the center. The atom that I'm going to be putting in the center is the one that can do the most bonds. So in this case, it's going to be the nitrogen because the hydrogen can only do 1 bond. Now, the next thing I need to do is I need to assume that everybody needs 1 pair of electrons or 1 bond to join everybody together. So if I wanted to put my hydrogen together to the nitrogen, I need to have 2 electrons because each bond has 2 electrons. So I need to connect everything together first. All right. So currently I've used up 2, 4, 6 out of my 8 electrons. I have 2 left over. Are we okay with that? All right, now the rule is with these 2 remaining electrons, I start by adding them to the outside shell, outside atoms, and I work my way inward. So I check to see if my outside atoms are stable, and if they are stable, then I move into my inner ones. So hydrogen, we know it's already an exception to the rule. It only needs 2 valence electrons, so that one's fine, and that one's fine. These guys are all fine. So now I take those 2 leftover electrons and I put them onto nitrogen. Now nitrogen's happy too because now nitrogen has its 8. So something to keep in mind when we're thinking about our terminology, these electrons that are between 2 atoms, these are known as bonded electrons. And then these are known as lone pairs. That's going to be really important in our next lesson that we'll do after break, which is on shapes. We need to know the difference between bonded and unbonded. So you might call them bonded and lone, or you might call them bonded and unbonded. Those both work. Are we okay with that so far? The other thing to keep in mind, and this is a personal preference, you don't have to do this, is that I like to draw bonded electrons as lines, so that way it indicates that that is in a bond. You are allowed to do that, that is fine. It means the same thing. So both of these would be marked as correct. I personally like the lines because the lines give me a very clear indication that these are bonded electrons and these ones are not bonded electrons. But it's not the end of the world if you don't do that. Either way is fine. Are we okay with that? All right, now I got to remember my exceptions to the rules. If I look at the periodic table, I'll know. All right, let me do carbon dioxide. That was a little more challenging. It kind of shows it in a bit more levels. All right, moving on. Okay. So let's now do carbon dioxide. We'll change the color. So carbon dioxide is CO2. All right. Now with that CO2, again, let's break it down. Now these steps here, you don't need to do it on the actual assessment. This is for me for teaching you guys. You will get faster at this and you won't need to do all this hoo-ha. Okay? But for the beginning, you need to do this properly. The other thing to keep in mind is that if you make a mistake on this Lewis structure, it's going to snowball, like I said. So if you're in doubt, do this. And if you have the time, do this. Now you guys are going to have 3 hours to do one exam. You have plenty of time. All right, so carbon, I only have one of those atoms. Carbon on the periodic table is in group 14, so it only has 4 valence electrons. So when I add that up, I have 4 to work with. And again, if we're not sure, go look at the periodic table, go figure out their columns. Group 14 is 4. We okay?
Group 14 is 4 outer electrons. Okay.
So I should actually give you guys a periodic table. I think I have, but I can't remember. So this is group 1, so it has 1 valence electron, everybody in there. This is group 2, it has 2 valence electrons. Then we don't worry about these guys, because these are transition metals. They're very complicated. You'll learn about that in level 3. This is group 13. They have 3 valence electrons. This is group 14, 4 valence electrons. 15, 5, 16, 6, 17, 7, 18, 8.
So these two would technically just always be the same number.
Yeah, so those numbers will always be the same. So yeah, so carbon's always going to be 4. So you're going to start memorizing them like I have. All right, so oxygen, you have 2 of them. They are in group 16, so you have 6 valence electrons. So 2 times 6 is 12. So total number of electrons that I'm working with is 16. Yeah? Okay.
Wait, how did you get 16, sorry?
2 times
12 or... R.
Man. I don't know how to explain addition to you.
That's...
You want me to get like the little beads instead of count? So they will provide you a periodic table. I'm forgetful and I forgot to print you guys off. Might have printed one off at the beginning of the year, but I can't remember. I don't know. You probably lost it anyway. I probably should print you another one. Okay, actually I do need to print you. I'm gonna think of it. Okay, so if I'm looking at the carbon and the oxygen, which one do you think will be the center? How many bonds can oxygen do? 2. How many can carbon do? 4. So carbon's going in the... It's okay. That's why we do this. All right. Oxygen's then 10.
Why would you total like on that chill?
3 and 4. Period workshop. It's okay, I'm recording the lesson.
Wait, how do you know when which one's bigger to
Okay, so remember you're adding yourself up to 8.
Yeah.
So you're thinking, okay, if I'm at 6, I need 2 more electrons to get to 8, so that I can only do 2 bonds with oxygen. In this case, I have 4 electrons, so I have 4 spaces for bonding. That's why carbon is our building block for life versus other elements which are smaller because they can't do as many bonds. So we can do lots of interesting patterns with carbon. You guys will learn that next year. All right, so we put our oxygens there and we assume we have to have 1 bond so that everyone stays together. Okay? So that process has given me 4 electrons already. So I minus my 4, so I currently have 12 electrons left over. We're being a little atomic accountants right now. All right, so now with my remaining 12, remember I'm going outside, working in to make sure everyone's full. So for this oxygen here, it has 2, 4, 6, sorry, 2, 4, 6, and now it has 8. So you see how oxygen is now full. So I've used up 2, 4, 6 electrons, so I'm subtracting 6, I have 6 more left. Honesty's making me a face that she didn't understand what that's. But do you want me to repeat it? Okay, I'm gonna do it again, so it's gonna be fine. All right, so I still have 6 electrons. Again, we go outside going in, so we're not gonna do anything to the carbon yet. We're gonna do something to the oxygen. So it has 2. I'm adding another 2. So that's 2, 4, and 6. So I've used up my remaining 6 electrons. I'm now at 0. And now my oxygen has 2, 4, 6, 8. It is stable. So both the oxygen and the carbon, both the oxygens are happy. The next thing to check is the carbon happy? So the carbon also needs 8. Right now when I look at it, it has 2, 4. It is not stable. So when this happens, you are going to move electrons from the outside of the molecule inside. So I am taking, and it doesn't matter which 2 you're taking off, I'm going to take the ends, that way it looks even. I'm taking that guy off, and I'm moving it to the center. I'm taking this guy off, and I'm moving it to the center. So now when I tidy this up, it should be O dot dot C dot 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 O dot 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 dot. Lots of dots. And that's how I know there's a double bond there. It doesn't matter where you put these electrons. If you draw it like dot 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 like that, that's also correct. The only thing I'm checking is to make sure you have the right number of electrons on each. All right, now you can see now why I like to draw the lines, because this looks a lot cleaner than the other one. You don't need to do it, but that one's easier on teacher's eyes. It's also going to make your life easier when you're trying to figure out lone pairs and bonded pairs. So that's why when we did the molecule for carbon dioxide, its shared electrons had 4 electrons. Because it had a double bond. All right. Trying to think, what time does this session end? Can't remember, because I only don't teach.
And your equals are the double bonds, right?
Yeah.
So if it was just singular, it would just be 1.
Yeah, it would just be 1 line. And if it was a triple bond, you'd draw 3. Yeah.
Gotcha.
Not too bad, eh?
Yeah.
All right. Let me tell you guys of some exceptions to the rules, so we know that. I know, chemistry, right? All right, exceptions. Okay. You already know one. So this is exceptions to be stable. Hydrogen, what do we need to be stable? 2. So remember that when you're doing your math and when you're double checking things. All right. The other one is beryllium and boron, and I need to look at them to try to remember. Go away. All right.
Hydrogen only needs 2 electrons.
Yeah, I think from memory, beryllium only needs 4. And boron only needs 6, I want to say. It's off the top of my head. So that's what they need to be stable. So for example, if you were doing boron with 3 hydrogens, so BH3, this would be the Lewis structure for that, and that's stable. 2, 4, 6. And then if we were doing the math to make sure we had the right number of electrons, there's 3 electrons coming from the hydrogen, and then from the boron, there's another 3. Yep. 6, and then that's 6 there. 2, 4, 6. You'll get faster at this, and you won't need to think about this as much. You'll also start to semi-memorize the molecules, that you'll be able just to plop them down like that. So that's what that one looks like. So don't just assume when you're drawing things, oh, it needs to have a lone pair of electrons because I need to get to 8, because that's actually not the rule for boron. It can be stable with 6. So you stop here. Also, you don't have 8. You don't have 2 more electrons on the count. So don't create matter out of nowhere.
BH4, but then you say I only want to say hydrogen. No, on the right? Yeah.
Oh, that should be a 3. Sorry. Good catch. So I had 3 electrons coming from the hydrogens, because there's 3 of them there. And then boron contributes 3 from its valence shell. So I had 6 electrons to work with. And that's where I'm getting the 2, 4, 6. So don't stick a lone pair of electrons on there because you think that's right. Because then you tell me that you've made 2 extra electrons somewhere. You're saying you have 8. Mm-hmm. So this number should always match that number. Right? And that's Lewis structures for you. The physicists learned something today. Yeah. Yeah. You did the chemistry exam, so some of the stuff would be, yeah. That's what I'm saying, like, the stuff that we do in level 3 chemistry compared to level 2, it's like, it's useful to have, but it's not necessary. A lot of our standards are very different. So if you want to drop into the level 3 chemistry course, you'll be fine. And I'll sign off on it. In fact, I think there's at least a quarter of my class right now in my level 3 course that didn't take level 2. So. All right, so for you guys, all right, I need to double check when this period ends, but you guys have some SciPep pages to work on just to practice it. I personally would skip the drawing of the atoms. That's why I haven't listed it on here, because I think it's not a useful use of your information. These 2 here are only doing simple molecules without double and triple bonds. This one obviously does the double and triple bonds. You don't need to do all of them. Just do what you need to do to feel confident. And then you're done. And I think my friend also made something on his website, so I have to go check it out and see. But yeah, cool. All right, so you guys have the remaining time to work on that. And then after the break, we will do shapes, just like primary school.